Hello everyone and welcome to my video tutorial on Introduction to Graph Theory using Python and NetworkX. This is the 7th class of the series, Cuts and Flow Problems. My name is Innocent Okoluko. Motivation. Flow problems have practical application in such areas as telephone lines, highways, railroads, oil pipelines, baseball elimination, airline scheduling, circulation demand problems, image segmentations, electronic circuit, etc. Therefore, it is important to know about them. Learning objectives. At the end of the class, participants should be able to explain the concept of flows, define and analyze a maximum flow problem, define, analyze and extract flow augmenting paths, define and analyze cuts in a capacitated network. Define, analyze and implement the forecasting algorithm. Content. Introduction to flows. Maximum flow problem. Cuts in a capacitated network. Forecasting algorithm. NetworkX example. We'll begin with introduction to flows. In a network of telephone lines, highways, roads, oil pipelines, water pipelines, gas pipelines, etc., it is important to know the maximum rate of flow that is possible from one station to another in the network. Specifically, consider a network of pipes where valves allow flow in only one direction. Each pipe has a capacity per unit time. This can be modeled using a vertex for each junction stroke location and a directed edge for each pipe weighted by the capacity. Given two locations S, T in the network, we may ask, what is the maximum flow per unit time from S to T? A capacitated network is a digraph with a capacity C bracket E greater or equal to 0 on each arc E and a distinguished source vertex S and sink vertex T. C bracket E greater or equal to 0 is the capacity of arc E. The distinguished vertices source has an in degree 0, meaning that nothing flows into the source, and sink has an out degree 0, meaning that nothing flows out of a sink. So everything flows from the source and everything ends at the sink. A flow F assigns a value Fe to each arc E. The inflow into a vertex V is denoted by F to the power of minus bracket V, which is the total flow on arcs entering that particular vertex V. The outflow from vertex V, denoted by F to the power of plus bracket V, is the total flow on arcs leaving vertex V. There must be some capacity constraints. The constraints are 0 less or equal to the flow of E less or equal to the capacity of E. What this simply means is that the flow along a pipe or the flow inside a pipe must be less or equal to the capacity of the pipe. It cannot be greater than the capacity of the pipe, otherwise there is a risk that the pipe is going to explode. Conservation constraints. For every vertex except the source and the sink, the quantity flowing into that vertex must be equal to the quantity flowing out of that vertex. We say a flow is a feasible flow if it satisfies the capacity and the conservation constraints, both of them, for all vertices inside the network, excluding the source and the sink. Source must only have outflow and sink must only have inflow. The zero flow assigns a zero to each arc, and this is also feasible, meaning that it is possible nothing is flowing through the pipe. That is okay. The only problem is when what is flowing out of a pipe is bigger than the capacity of a pipe. The value val f of a flow is the net flow. That is, val f is equal to inflow minus the outflow into the sink. Is what is indicated by this. So you can see that for every other vertex that is not a source or a sink, this val f is supposed to be 0. Let's take our first example to make things clearer. In the network below, the flow value is shown in parentheses. So in graphs, we are going to see that the flow value will be written side by side the capacity of the network. So there are very different notations for writing this in several books, and we are going to see some of them so that you don't get confused when you see a different notation in another book. Flow means that this is the current quantity that is flowing through this pipe at the moment. If you look at all of them, you discover that the flow can never be greater than the capacity. And if you look at them, you also discover that what is flowing into a node is equal to what is flowing out of a node, except at the source, which is S, and at the sink, which is T. So this particular flow assigns for the arc SX is the same thing as VT, and that is 0. And the other flows are assigned to 1. So you see this is 0, this is 0, and the rest of them are 1. This is a feasible flow. And we can see that the value at the sink is inflow, which is F minus, that is 1, minus outflow. Of course, nothing flows out of a sink, 0, and that's what gives us that 1. So what we are trying to study in this chapter is how to maximize the flow. What we see here now is not a maximum flow, because you can see that this side is 0 already, and the reason is because 0 is coming out of a source, 1 and 0. It is not possible that what is coming out from the source is different from what you have at the sink. They must be the same. If we look at this modified flow graph on the other side, we are seeing here the network. The flow F prime with F Vx, Vx equal to 0, and F prime E equal to 1 for all E, all edges that are not Vx, has a value of 2. So suppose we open this valve and make it 1, and we open this valve and make it 1. So we can see that if 1 comes here, it is 1 that must also come out from here. And if 1 comes to V, it is 1 that must also come out of V. So we have 1 here. This 1 comes to X, goes to Y, and we have 1 here. So 1 plus 1 is equal to 2. 2 comes out of a source, and 2 goes into the sink. So the flow, we say this flow is maximal, but at the same time we cannot call it the maximum flow. So the process of determining the maximum flow is something we want to learn about in this class today. Now let's take a second example, example 2. In the capacitated network D shown on the right hand side, the first number is the flow and the second number is the capacity. So you see in this second example, the flow is not written in bracket, meaning that some books will actually designate it like this. It doesn't have to be written in bracket like the previous example. So if you see something like this in another book, it is also okay. Now, how do you even determine when you see a network with 2 parameters like this? You see a graph with 2 parameters like this. How do you know which is the flow and which is the capacity? Without being told whether it is in parentheses or not, just look at which one is bigger for all of them. In this case, the one on the right is always bigger for all of them. The bigger one will be the capacity, either bigger or equal, but not less than. So you can just determine from any graph which one is the flow and which one is the capacity. The question is saying identify the source and the sink. Another thing is you may not explicitly see S and T on the graph indicating source and sink. How do you know which one is source and sink? The source is the node for which edges are going out but they are not coming in. So if you see node 1 for instance, you will discover that all the edges that are coming out from node 1 are directed elsewhere. Nothing is coming into node 1. So automatically you can detect that node 1 is the source. If you look at node 2, something is coming in, something is going out. A sink node cannot have anything going out. The same thing with node 3. Node 4 is the sink because all the nodes are coming into node 4 and nothing is going out. So we have solved the first problem. Second is, what is val F? Val F is the total number of flows that are coming into the sink. And what would that be? It's just 3 plus 0, which gives us 3. Does F satisfy the conservation constraints? We check that out. Conservation constraints means that whatever is flowing into a node that is not the source or the sink must be equal to whatever is flowing out. So in node 2 we have 3 coming in, we also have 3 going out. In node 3 we have 3 coming in, we also have 3 going out. In node 4 we have 0 coming out, 0 going to T. So this is yes, the conservation constraint is satisfied. Does F satisfy the capacity constraint? The capacity constraint means that the flow must be less or equal to the capacity. So if you watch all of them, everything is less or equal to. This is less or equal to. So again we say F satisfies the capacity constraint. So is F feasible? Of course it's feasible. We say a flow is feasible if it satisfies both the conservation constraints and the capacity constraints. So this again is a yes. Now let's look at maximum flow problem. First, what is the maximum flow? It is a feasible flow F in a capacitated network such that the value of the flow is as large as possible. That's the maximum flow. And the maximum flow problem is the problem of finding that feasible flow such that its flow is maximum. Now we describe something called the flow augmenting path. When a flow F is a feasible flow in a network N or in a graph G or D, whatever, a flow augmenting path is a source to sink path such that for each edge E in P in that path, if P follows the edge in the forward direction, then the flow is less than the capacity, and if P follows E in the backward direction, then the flow is just greater than 0. Tolerance of the flow augmenting path P. Let delta equal to the flow minus the capacity when the particular edge is forward on P, and let delta just be equal to the flow when E is backward on P. Then we can define the tolerance of P as the minimum of the particular delta that we obtain for this particular flow augmenting path. So what we are going to do here is we are going to calculate the tolerance E for every one of the edges for the path. And when we look at all the delta E that we calculate for this particular flow augmenting path, we pick the smallest one of them, and that is the tolerance. So a flow augmenting path leads to a flow with a larger value. The tolerance is positive and the amount increases the flow value. If P is a flow augmenting path with tolerance delta, then changing the flow by plus delta on edges followed forward by P, and then subtracting the tolerance on edges followed backward by P produces a feasible flow F prime, whose value is val F plus delta. We see an example and it will become clearer. So let's look at example 3. Find flow augmenting paths in the network shown below, where the first number is the capacity and the second number is the given flow. So we are seeing another example here now of notation, where the capacity is written on the left side and the flow is written on the right side. Of course, you can deduce it by looking at the values and determine which one is the flow and which one is the capacity. So when we solve this problem, things become clearer. We can find a flow augmenting path by inspection and augmenting the existing F. First of all, if we look at the current flow of the system, you can determine it from what is flowing into the sink. This arc is 3 flowing into the sink, and this arc is 6 flowing into the sink. So if we add 3 plus 6, we get 9. The current flow is 9. So we want to maximize the flow and see how far we can get. So we will use the notation delta. This is what I just described. We will use the notation delta E equal to capacity minus flow if the arc is going forward, as the arrow is pointing to the next node. Otherwise, we will use the notation delta E is equal to the flow if the arc is going backward. You see, this is an arc that is going backward already, and this may well be an arc that is going backward depending on what you select, which flow augmenting path you select. So the excess flow capacity is going to be the minimum taking over all arcs of that particular flow augmenting path I will choose. Now, one flow augmenting path is, we take 1, 2, 3, 6. So we just take this set of edges that goes from source to sink. Like I described flow augmenting path before, just pick a sequence of edges that leads from the source to the sink. We already have one on top. So P1, we call this flow augmenting path P1 equal to 1 to 2 to 3 to 6. Can we maximize the flow there? Of course we can. So how do we do that? So we now say delta 1, 2 from 1 to 2 is the capacity minus the flow equal to 15. Delta 2 to 3 from 2 to 3 is the capacity minus the flow equal to 3. And we say delta 3 to 6 is the capacity minus the flow equal to 7. So the reason why we are subtracting the flow from the capacity is because all the arcs here are forward arcs. All of them are going forward. None of them is going backward. Now we are going to take the minimum of everything we calculated here. We have 15, which is large. We have this 3, which is the minimum, and we have 7. So we take the minimum. Delta is now equal to 3. And what do? We add this particular 3 to the flow, meaning that this flow that was originally 6, if we add 3 to it, is going to become what? 9. And we can now add 9 plus 3, and that gives us 11. So if we continue, so we can use P1 to increase the given flow 9 to 9 plus 3 equal to 12. What we calculated, the tolerance we chose was 3. That was the minimum. So if we add it to the current flow, we get 12. And how did that happen? After you finish calculating this for any flow augmenting path, what you should do is add it to the current flow. So this will become 8. This will become 11. 8 plus 3 is 11, which makes this already saturated, so we won't deal with this again. And this will become 6 plus 3 equal to 9. 9 plus 3 is what gives us this 12. We are not done yet because there are some arcs that we still have not considered. Another flow augmenting path is 1 to 4 to 5 to 3 to 6. So we are going to pick these sets of arcs. And the reason why we are avoiding this is because the capacity is already equal to the flow, so you can't deal with it anymore. Anything you do beyond this is going to burst the pipe if your calculation is bigger. We can't improve it further. So let's take that, and this is what the flow augmenting part looks like. You can see that this one is a returning edge, is not a forward edge. How do we calculate that? From 1 to 4 is 10 minus 4 equal to 6. From 4 to 5 is 7 minus 4 equal to 3. From 3 to 5 is negative. It's not a forward flow. Or we could have just said 5 to 3. It's negative. So in that case, we just take the flow according to our previous description of the algorithm, rather than doing the subtraction. And finally, 3 to 6 is 9 minus 13, which gives us 4. And what is the minimum of what we have here? It is 2. So we can use P2 to further increase the previously increased flow to 14. So what you do is just add 2 to all of these parts, but subtract 2 from this one, in which case the flow here is going to be 0. And this one is going to be 9 plus 2, 11. We did not consider this, already saturated. This one is going to be 6. This one is going to be 6. And what do we have? 11 plus 3 gives us 14. So we have increased the previous flow from 12 to 14. Now let's look at cuts in a capacitated network. A source or sink cut denoted by bracket S, T, or we use the square brackets, they are the same thing. So in a capacitated network, a source sink cut consists of the edges from a source set to a sink set, where S and T partition the set of vertices with the source inside this set of sources or source set, and the terminal node or the sink node inside the set of terminal nodes. Now what we are trying to do is expand the concept of source and sink to include other vertices in the graph. Not just one vertex is the source, but a set of vertices is the source, and not just one vertex is the sink. Rather, a set of vertices in the sink is in the sink. So if you still remember bipartite graphs where we have a set of nodes that are partitioned into two sets, and one set connects all the nodes in one set, connects to all the nodes in the other set without the nodes in one set connecting each other. Now this is not a bipartite case, because in this case the set of nodes in the source set can connect with each other, and the set of nodes in the sink set can also connect with each other. Thus, we can say the cut, which consists of the set of edges such that all these edges are inside the edges of the graph, where this node is in the set of sources and this J node is in the set of sinks, is a capacitated network and a feasible flow defined on a set of arcs. We will now define the capacity of a cut, which is the sum of the capacities of all forward edges in the cut set. Forward edges only, not backward edges. We will describe the minimum cut. If this capacity does not exceed the capacity of any other cut, you can have several different cuts depending on the way the source set and the sink set is arranged or selected. So whatever cut you get, if the capacity does not exceed the capacity of any other cut, then we say it is a minimum cut. We also define the flow along the cut, not just the flow along an edge this time. It has become more elaborate. It is the sum of the flows along all arcs in the cut. Obviously, following what we described before, that the flow must be less or equal to the capacity, we can also say the flow of a cut must be less or equal to the capacity of a cut. the flow can be 0, in which case nothing is flowing, and that is acceptable. So let's look at an example. In the graph shown below, the inflow into the sink and the outflow from the source are 8, which is the current flow value. Of course, you can see that 7 plus 1 equal to 8, 3 plus 5 equal to 8. So if the source set consists of the nodes 1, 2, 3, and the sink set consists of the nodes 4, 5, 6, determine the following. The flow, ST. Now, when you want to do this, one strategy is to draw the graph in such a way that you can easily determine which nodes make up the source and which nodes make up the sink. In this case, our source was 1, 2, 3, so I color them red. 1, 2, 3. And the flow is all the edges that are coming from the source to the sink. We have this edge, we have this edge from the source to the sink. So it is easy for us to just calculate the flows, is it not? By looking at this, we know the flows are 3, 4, and 7, which gives us 14. What about the flows from the sink to the source? We have 6 plus 0, which gives us 6. Third question is flow value, which is flow from source to sink minus flow from sink to source. So when we start talking about cuts, that is when the idea of something flowing out from the sink set to the source set. In ordinary flow networks, nothing is supposed to flow from the sink to go anywhere. But when we talk about cuts, that is a possibility. So we now say the flow value is what? 14 minus 6, and that gives us 8. So what is the capacity? Just like the way we can do that, remember capacity is forward edges only. The capacity from S to T. Simple. We just take the capacity 7, take the capacity 4, and take the capacity 8. And what do we have? 7 plus 4 plus 8, and that gives us 19. In the same way, we can also talk about the capacity from the sink set to the source set, and that's straightforward enough. 9 plus 4, that gives us 13. So the last question said, what is the capacity of the cut? The capacity of the cut is indicated by from source to sink, only forward edges, and that gives us 7 plus 4 plus 8, which is 19. So before we go, we'll consider an algorithm. It is called the Fulkerson algorithm. It is a greedy algorithm that computes the maximum flow in a flow network. Let D, VE be a graph, and for each edge from U to V, let C bracket UV be the capacity and F bracket UV be the flow. Find the maximum flow from the source S to the sink T. After every step in the algorithm, the following is maintained. Capacity constraints must be maintained whatever you do. And the capacity constraint says that the flow along an edge can never be greater than the capacity of the edge. It can only be equal, it can be 0, those are accepted. Skew symmetric constraints. The net flow from a vertex U to a vertex V must be the opposite of the net flow from V to U. Conservation constraints. The net flow to a node is 0 except at the source and at T, which is the sink, meaning that for every node that is not a source or a sink, the flow coming into the node must be equal to the flow going out of the node. Val F. The flow leaving from S must be equal to the flow arriving at T. All of these constraints must be maintained as we perform the forward forecasting algorithm. However, we have already done something based on this algorithm when we were looking at the maximum flow in the first example that we considered on maximum flow problems. So it's about the same thing. It's not going to be much different. Formally, we describe the forward forecasting algorithm as follows. Algorithm forward forecasting: D equal to VE C S T. You already know what those mean. Given a network D equal to VE with a flow capacity C, a source node S, and a sink node T, compute a flow from S to T of maximum value. Input: we have the graph, we have the capacity, we have the source, and we have a sink. Output: maximum flow from S to T. Step 1. Set the flow for all edges to 0 if it's not already given. If you are given a network that does not have anything at all, set all the flows to 0 to begin with. The algorithm is going to start increasing it incrementally until it gets to maximum. But if you have already been given a network with some flows that are there already, you may not need to set them to 0. Rather, what you need to do is maximize on the values you already have there. While there is a path, that's a flow augmenting path from the source to the sink, such that the capacity is greater than 0 for all edges inside that flow augmenting path, we are going to do two things. Find delta P, which we did before in the example we saw previously. So we are going to look for delta P for all the edges, and then we are going to take the minimum. And for each edge UV in the flow augmenting path, we are going to send the flow along the path. So what we do is take the residual, the minimum that we calculated before, and add it to all the forward going edges in the path. Subtract it to all the backward going edges in the path. When we have done that completely and all the edges are saturated, you can end the algorithm. It's a very simple algorithm, and we have done it before in this class. So we are going to repeat it again in a formal way. Now, the same graph that we saw before, we are going to apply the forward forecasting algorithm to determine the maximum flow in the graph. So it is the same thing we have done previously, but this time around we are going to do it the forward forecasting way. Initial flow is 9, as you can see from the graph. 6 plus 3 is equal to 9. So we don't need to set all the flows to 0. Otherwise, you give yourself more unnecessary work. Eventually, you'll come back to the maximum flow, but that's not necessary. So we are going to start with what we already have. Step 1. We take a path. 1, 2, 3, 6. So we have 20 minus 5, 15. 2 to 3, 11 minus 8, 3. 3 to 6, 13 minus 6, 7. And which one are we going to pick? The minimum. That gives us delta 3. So we'll now send the flow along the path. Since all the paths are forward paths, we are going to add 3 to every other flow that you already have here. So 3 plus 5 gives us 8. 3 plus 8 gives us 11. 3 plus 6 gives us 9. So I colored this edge as red because we are never going to come and do anything here again. It's already saturated. I also color this edge red because it is already saturated right from the initial time that this network was given to us. This is already full. We have succeeded in increasing the flow from 9 to 9 plus 3 equal to 12. That's not all. While there is still a path, return to step 1. So we'll go back again. And this time around, we are going to take another path. So we take 1 to 2, to 5, 5 to 3, and 3 to 6. So we progress with our calculations again. Delta 1 2 is 20 minus 8, 12. That's quite large. 2 to 5 is a negative edge. It's coming back. So we are not going to do a subtraction. Rather, we'll just take the 3 whenever there is a negative edge. 5 to 3 is another negative edge. We are not going to do a subtraction. We just take the 2. And 3 to 6 is 13 minus 9, which gives us 4. So what is the minimum among these? 2. We send the flow along the paths. We are now going to add 2 to 8, which gives us 10. And because this is a negative part, we subtract 2 from 3, which gives us 1. Because this is negative, we subtract 2 from 2, which gives us 0. And we add 9 to 2, which gives us 11. So I have colored this red because we can't go here again. The flow is 0. When the flow is 0, we cannot come back here. This one is saturated, this one is saturated, and this one is saturated. So we have succeeded in increasing the flow from the original 9 to 14. 11 plus 3 equal to 14. Now let's look at this diagram we have here. Is it possible for us to increase the flow further? Suppose we take 1 to 4 and 4 to 5. The road is blocked, isn't it? Even if we follow this way here, we cannot pass here. If we say we want to follow 5 to 3, we cannot pass here. If we say we want to follow 5 to 6, we cannot pass here because they are already saturated. Meaning what? We have come to the end of our algorithm and we succeeded in increasing the flow from 9 to 14 like what happened before. And that is the maximum flow, and in this case we end the forward forecasting algorithm. Before we go, let's look at a NetworkX example. We are not going to write the forward forecasting algorithm from scratch here. Rather, what we are going to do is see how to use NetworkX to determine the maximum flow in a network. So we'll call this program flow0.py to demonstrate flows and cuts in NetworkX. As usual, we'll do our preliminary imports. We'll create a graph. G equal to nx.diagraph. We add edges. In fact, instead of wasting your time adding nodes, if you already have the edges, just add the edges. The nodes will be automatically assumed. So we say g.addEdge 1, 2, from 1 to 2, capacity equal to 20, flow equal to 5. 2 to 3, 1 to 4, 3 to 6, 3 to 5, 4 to 5, 5 to 2, 5 to 6. Now, if you don't understand what is going on here, if you don't know anything about graph theory or NetworkX, and you are starting with this lecture, you may not be able to understand because I am not going to go back to explain the preliminaries. What I will advise you to do is look at the previous videos of this class where we actually taught NetworkX from scratch. Then you can be able to appreciate what we are doing at this stage. Now, for us to have the graph look like exactly what we want it to be, we can put the node positions in Cartesian coordinates. So we set the positions. 2 is 5, 10, 3 is 8, 10, 4 is 5, 2. Then we can set the figure to plot.figure. And then we set a title, graph G. We can now draw the NetworkX nodes. G, pose, node size, we want to make it big, 800, node color equal to green. And then we can draw the network labels as usual. We now want to draw the edges. But this time around, we don't just want to draw the edges using the edge label alone, the capacity. Rather, we want to draw the capacity and the flow value, so there will be two values. So take note, when we define the edges of the graph, we actually defined the flow value along with the capacity of the edges. So we use two of them in drawing the edges as we see here. So we want to get the width, which is the edge 2, capacity. If you don't understand what is going on here, watch the last two videos. We also want to extract the flow, which we define. So we say draw network X edges, G pose edge list, width equal to 5, arrow size equal to 30. We actually don't want to show how large the capacity is in the diagram by making the edges big or small. Rather, we want to use a specific width for uniformity, because that's not what we want to demonstrate. So, but when we want to create the edge labels, we are not only going to use the width this time around, we concatenate it with the flow value. So we can have two values with a comma in between them, and then we can draw it as usual. So let's calculate the maximum flow. We use the NetworkX function max flow. Put the graph inside and source node, sync node, the flow dictionary, which is a parameter that is going to be returned, and the flow value, which is an integer value that will be returned, and we discover that it's actually 14, which we calculated. We can also obtain the minimum cut for the particular graph, minimum cut from node 1 to node 6, and we can print out the cut value and print out the cut partition. Show the graph. So we are going to go to Visual Studio Code and run this program and see exactly what it produces. So here we are in Visual Studio Code. This is the program we just described. I will now click it to run. Okay. So this is what we get out from the plot. And you can see that this is exactly the graph that we're actually looking at and trying to solve, the original graph. Now I'm going to minimize this window so we can see the parameters that were returned from this plot. So if we look at the program, when we did calculate the maximum flow, we printed out the flow dictionary and we printed out the flow value. This is the flow value here, which is 13, which we calculated. And these are the parameters we got: 1 to 2, 11, to 4, 3, 2, to 3, 11, 3 to 6, 11, to 5, 0. We still remember this: 4 to 5, 3, 6 goes nowhere, 5 to 2, 0, to 6, 3. Now some of the parameters here are not very clear to me, okay, but the important thing is our flow value was 14 and it is the same as what we calculated with our hand. Our cut value is equal to 14, and our cut partition was, the system automatically partitioned 1, 2, 4, 5 in one set and 3, 6 in another set. So we have come to the end of the class today. Our bibliography remained the textbook of Balakrishnan, Edward L. Platt, Filippo Mensah, and other materials. Be sure to check out my YouTube video tutorials and other numerous online tutorials. So please like, share, comment, and subscribe for more videos. Thank you, and see you in the next class.